Hi everybody, welcome back. In this video, we're going to formalize the data processing steps that are typically used prior to building and training models. To facilitate this, we're going to use a public data set from the UC Irvine Machine Learning Repository, and we're going to spend some time getting familiar with the data and preparing it for analysis. To do that, we're going to take advantage of two Python packages called Seaborn and Pandas, which are often used to help manage and explore data prior to training a model. So before we get started, let's just quickly preview the topics that we plan to cover. We're going to learn how to read a data set into a Pandas data frame that will allow us to easily manage and process the data in various ways. We'll also learn some techniques that can be used to clean a data set that may contain incomplete entries. We'll then show how you can easily explore the data set using Seaborn and Pandas to get a better feel for what the data looks like, and also how the various features may be correlated. We'll then explain how to split the data set into train and test components, which is a fundamental step in training and evaluating models. And then we'll conclude the notebook with an example of how to scale feature data, and we'll demonstrate how this can easily be implemented using a normalization layer in Keras. So let's go ahead and get started, and we'll begin by loading a data set from the Machine Learning Repository at UC Irvine. If you're not already familiar with this repository, this is a really great resource where you can access and use public domain datasets to experiment with. This particular dataset contains attribute data from automobiles built in the 1970s, such as the number of cylinders, the displacement of the cylinders, the horsepower of the car, and so forth, as well as the MPG of each vehicle, and we can use these features to help predict the fuel efficiency of the car measured in miles per gallon. I've previously downloaded this dataset to my local system for this video, but as you can see in the commented section, Keras allows you to easily access the data directly by specifying the appropriate URL. So the first thing that we're going to do here is read the data into a Pandas data frame using readCVS. And notice that we're supplying column names, since that makes it much easier to see what we're doing. If you're not familiar with Pandas data frames, you can just think of them as a tabular type of data structure with some very convenient methods that allow you to process and examine the data. When you're working with any kind of data set, it's important to make sure that the data set doesn't have any unusual or missing entries in it. In this section, we're going to demonstrate one of the most common techniques that you can use to clean a data set. We're going to use the isNA method in Pandas to determine which fields might have missing values. And as you can see below, there are just 6 missing values in the horsepower column, so we can simply remove these from the data frame using the dropNA method. Another useful data frame method is info, which provides a useful summary of the data frame as shown below. Now that we've cleaned the data set, removing partially populated records, let's take a look at a couple of methods that are commonly used to explore data sets. The first one makes use of the core method in Pandas that determines the correlation between the features in the data set. If we pass those results to the heat map method in Seaborn, it produces the following results in the form of a matrix. The numbers in each entry of the matrix tell us how the corresponding features within the dataset are correlated. So this is one way to get a quick sense for the relationship between the features in a dataset. Another very informative type of plot that's similar can be created using the pairplot function in Seaborn. Here you can pass in any number of features from the data frame, and it produces a nice plot of the joint distributions of each feature along with kernel density estimation plots along the diagonal. These KDE plots are essentially smoothed histograms of the individual features. And you can see that there's some clear relationships between some of the features and the MPG of the vehicles. Exploring the data in this way can give you a very good sense for which features might be useful predictors based on the amount of correlation they have to the target variable. This is also an easy way to determine if there are any outliers in the data, which can be very informative as you develop and test your model. Now that we've explored the data set, we're going to split the data into test and train components as shown below. The training data is going to be used to train the model, and the test data will only be used to assess how well our final model performs on data that it's never seen before. It's very important that you always reserve and isolate a percentage of your data set so that you can evaluate how well your model generalizes. We'll talk more about this later in the course, but we just wanted to emphasize that this is a very important step. One convenient way to split the dataset using Pandas is to randomly sample the dataset and specify a fraction such as 0.8 that you want to retain as the training dataset. And this is what the first line accomplishes below. The remaining 20% that we're going to reserve for test can be identified using the drop method as shown here. When we print out the shape of both of these data frames, you can see that of the nearly 400 entries, 80% have been reserved for train and 20% have been reserved for test. There are a number of ways in which you can split data sets into test and train, but it's important to remember to always randomly select samples so that the original ordering doesn't introduce any bias in the data. For example, if the data set was ordered by the country of origin, this could introduce a very unbalanced distribution between train and test unless you randomly select the samples from the data set. Another useful thing that you can do is to compute some statistics on each of the features in the data set, which you can accomplish with the following line of code. Notice that the various quantities vary by as much as 3 orders of magnitude, and that's generally not a good thing when you're training machine learning models. So we're going to go ahead and fix that in just a little bit. In this particular data set, the target value, which is in miles per gallon, is also included with all the features. So to keep things clean, we're going to separate the target values from the features. The features are typically stored in a variable called x, and the target values are stored in a variable named y. And we can split these apart using the pop method. The way this works is that we're going to make a copy of the train data set and the test data set and set those equal to xtrain and xtest respectively. And then we're going to pop off the MPG field from both of those data frames and set those equal to ytrain and ytest. So this effectively strips the MPG field from the feature data and stores it as the target variable in ytest and ytrain. So now when we print the statistics for xtrain, you can see that the MPG field has been removed. The final section of this notebook deals with feature scaling. As we showed above, the various features in our dataset have very different numerical values, and it's often recommended to normalize the features in some way that puts them on a similar numerical scale. Various methods can be used to accomplish this, but normalization and standardization are the most commonly used methods. Normalization usually refers to min-max scaling, where each feature is scaled to the range 0 to 1, as shown in the first equation below. Another method, called standardization, also referred to as z-score scaling, assumes that the original data is normally distributed and scales the features to have 0 mean and a standard deviation of 1. And just to be clear, with either method, each feature is scaled independently from the others. And the scaling factors, such as the computed mean and standard deviation of each feature, should be computed from the training data only, but then applied to all of the data. Thankfully, Keras now provides a normalization layer that automatically performs feature-wise normalization of the input features. In other words, we don't need to write our own functions to manage this conversion. We simply need to specify a normalization layer and pass it one or more features that we want to use in our model. The name of the layer in Keras is a little bit confusing because normalization typically means normalizing the data between 0 and 1, but the normalization layer in Keras actually performs z-score scaling on the feature data. So you can think of the normalization layer as an extra layer that pre-processes the input data prior to the first layer in the network. So now let's take a look at how to create a normalization layer using a single feature as a simple example for the syntax required. First, we're going to convert the horsepower feature in the data frame to a NumPy array. We then create a normalizer object with an input shape of 1, since this is for a single feature. And then we use the normalizer object to call the adapt method, which completes the implementation of the normalization layer. And then here we're showing that we can print out the parameters associated with this layer. This might feel a little bit abstract at this point, but in the next video coming up, we're going to continue with the topic of regression, and we'll be using this dataset to work through several examples in Keras, and we'll show you how to add a normalization layer to those network architectures. Thanks so much, and we'll see you next time.